Today we're going to explore a fascinating question. Why does kneading dough make it stretchy and elastic instead of stiff and crumbly? This involves some beautiful physics and chemistry. Think about this for a moment. When you knead dough, you're applying mechanical stress, you're literally beating it up. Yet somehow, this makes it more elastic and stretchy. Why doesn't it just fall apart? Let's start with the basics. Dough is primarily a mixture of flour and water. Flour contains two key proteins, Gliadin and glutenin. These proteins are dormant in dry flour. When water is added to flour, these proteins hydrate. Gliadin provides viscosity and extensibility, while glutenin provides elasticity and strength. So what exactly happens at the molecular level when water encounters these proteins? Let me explain the hydration process. Water molecules, which are polar, surround the protein molecules. They form hydrogen bonds with various sites on the proteins, causing them to unfold and become mobile. Once hydrated, Gliadin and glutenin can interact with each other. They start forming disulfide bonds, which are strong covalent bonds between sulfur atoms in different protein chains. Now here's where it gets really interesting. When you knead the dough, you're not just mixing it. You're actually building a three-dimensional protein network called gluten. Imagine a tangled mesh of protein chains, connected by various bonds. This is the gluten network. The circles represent protein nodes, and the lines represent bonds connecting them. The gluten network is held together by several types of molecular interactions. Let me break these down for you. First, disulfide bonds. These are covalent bonds between sulfur atoms in cysteine residues. They're very strong, with bond energies around 250 kilojoules per mole. Second, hydrogen bonds. These form between nitrogen-hydrogen groups and oxygen-carbon groups. They're weaker, around 20 kilojoules per mole, but there are many of them. Third, hydrophobic interactions. Nonpolar amino acid residues cluster together to avoid water, creating additional structural integrity. Now let's address the key question. Why does mechanical stress make the network stronger instead of breaking it apart? When you knead dough, you apply directional stress. This causes the randomly oriented protein chains to align along the direction of stress, like combing tangled hair. Before kneading, the protein chains are randomly oriented. This is inefficient for load bearing. After kneading, the chains align along the stress direction. Now they can share the load much more effectively, like parallel cables in a suspension bridge. But here's the really clever part. During kneading, bonds are constantly breaking and reforming. This is called dynamic bond exchange. When you apply stress, some of the weaker bonds, especially hydrogen bonds, break. But because the proteins are now aligned, these bonds can reform in more optimal positions. Each cycle of breaking and reforming allows the network to reorganize into a more stable, lower energy configuration. It's like annealing in metallurgy. Let me give you an analogy. Imagine you have a bundle of loose threads. If you just twist them randomly, they won't be very strong. But if you align them and twist them systematically, you create a rope that's much stronger than the individual threads. Loose, unorganized threads have little strength. They slide past each other easily. But when twisted together into a rope, the same threads become incredibly strong. This is exactly what happens in gluten networks during kneading. Now let's get quantitative. I want to estimate how much energy is involved in this process and how many bonds we're talking about. Consider a typical bread dough. Let's say 500 grams of flour with 60% hydration, so 300 grams of water. Flour is roughly 10 to 15% protein by mass. Let's use 12%. So we have 60 grams of protein in our dough. 500 grams times 0.12 equals 60 grams of protein. The average molecular weight of gluten proteins is around 30,000 daltons, which is 30,000 grams per mole. So we have 60 divided by 30,000, which equals 0.002 moles of protein molecules. Using Avogadro's number, that's 0.002 times 6.02 times 10 to the 23rd. This gives us about 1.2 times 10 to the 21st protein molecules. That's over a sextillion molecules. Now let's estimate how many bonds form. Each protein molecule can form multiple bonds with neighboring molecules. A reasonable estimate is that each protein molecule forms 5 to 10 bonds with neighbors. Let's use 7 as our average. That gives us 1.2 times 10 to the 21st times 7, which equals about 8.4 times 10 to the 21st bonds. However, each bond connects 2 molecules, so we need to divide by 2 to avoid double counting. So we have approximately 4.2 times 10 to the 21st unique bonds in our dough network. Now let's estimate the total binding energy. We'll consider both hydrogen bonds and disulfide bonds. Most bonds are hydrogen bonds. Let's assume 90% are hydrogen bonds at 20 kilojoules per mole, and 10% are disulfide bonds at 250 kilojoules per mole. For hydrogen bonds, that's 3.78 times 10 to the 21st bonds times 20 kilojoules per mole divided by Avogadro's number. This gives us about 125,000 kilojoules from hydrogen bonds. For disulfide bonds, that's 4.2 times 10 to the 20th times 250 kilojoules per mole divided by Avogadro's number. This gives us about 174,000 kilojoules from disulfide bonds. The total binding energy is approximately 300,000 kilojoules or 300 megajoules. That's equivalent to the energy in about 7 kilograms of TNT. So let's return to our original question. Why doesn't mechanical stress make the dough stiff and crumbly? What's special about this system? The key is water. Water acts as a plasticizer. It sits between protein chains and allows them to slide past each other while maintaining connections. Without water, the proteins would indeed become stiff and the dough would be crumbly. Water provides the mobility needed for dynamic bond exchange. Here's a simplified view. The red circles are protein chains, and the blue circles are water molecules. Water sits between the proteins, allowing them to move relative to each other. This combination of properties makes dough viscoelastic. It has both viscous properties, like a liquid, and elastic properties, like a solid. The viscous component means dough can flow and deform permanently when you apply stress slowly. This is why you can shape it. The elastic component means it can recover and spring back from rapid deformation. This is why dough bounces back when you poke it. The behavior of dough depends critically on the timescale of the applied stress. Let me explain this fascinating phenomenon. If you pull dough quickly, the bonds don't have time to rearrange. The network resists elastically and can even tear if you pull too hard. If you pull slowly, the bonds have time to break and reform in new positions. The dough flows like a very thick liquid. Kneading operates at an intermediate timescale, fast enough to align proteins, but slow enough to allow bond reorganization. This is the sweet spot. There's actually a dimensionless number that describes this behavior. It's called the Deborah number, named after the biblical prophetess Deborah. The Deborah number is the ratio of the material's relaxation time to the observation or deformation time. When the Deborah number is high, meaning deformation is fast compared to relaxation, the material behaves like an elastic solid. When the Deborah number is low, meaning deformation is slow, the material behaves like a viscous liquid. For dough, the relaxation time is on the order of seconds to minutes. This is why kneading, which typically involves deformations over similar timescales, is so effective. Temperature plays a significant role in gluten network formation. Let me explain the thermal effects. At higher temperatures, molecular motion increases. Bonds form and break more rapidly, speeding up the network development. However, if the temperature gets too high, above about 60 degrees Celsius, the proteins begin to denature irreversibly. The network actually weakens. The optimal temperature for kneading is typically 24 to 27 degrees Celsius. This provides good mobility without risking denaturation. Here's an interesting question. Can you knead too much? Yes, you can, and here's what happens. If you knead for too long or too vigorously, you can break disulfide bonds faster than they reform. The strong covalent bonds that provide structure are destroyed. The network becomes overly extensible. It can stretch but won't hold its shape. The dough becomes sticky and slack. This is more common with machine mixing than hand kneading because machines can apply much more intense mechanical stress. Now let's talk about salt. Salt isn't just for flavor. It plays a crucial structural role in gluten networks. Salt ions, particularly sodium and chloride, shield electrostatic repulsion between negatively charged regions on protein chains. With reduced repulsion, proteins can pack more tightly together, increasing the number of bonds and making the network stronger. A typical bread dough contains 1.8 to 2.2% salt by flour weight. This is just enough to strengthen the network without making the dough too tough. Let me give you more details about the molecular structure of the proteins themselves. This will help you understand why they behave the way they do. Gliadin proteins are relatively compact and globular. They're rich in the amino acid proline, which creates kinks in the protein chain. Glutenin proteins are more extended and fibrous. They can form very long polymers through disulfide bonds, creating the backbone of the network. Different wheat varieties have different ratios of gliadin to glutenin. High-protein bread flour has more glutenin, giving stronger dough. Cake flour has more gliadin, giving softer, more extensible dough. It's instructive to compare gluten networks to other biological polymer networks. This gives us perspective on what makes gluten special. Gluten networks are similar in principle to collagen networks in skin and actin networks in muscle. All are dynamic protein networks that respond to mechanical stress, but they're very different from rigid polysaccharides like starch or cellulose, which don't have this dynamic bond exchange capability. What makes gluten special is that it undergoes reversible bond exchange at room temperature. Most biopolymer networks require heating or enzymatic action to reorganize. Understanding gluten network formation has important industrial applications beyond baking. Let me give you some examples. Vital wheat gluten is concentrated gluten protein used to strengthen dough in commercial baking and to make meat substitutes. Seitan, a popular meat alternative, is essentially pure gluten. Its chewy texture comes from the dense protein network we've been discussing. Gluten-free baking is challenging because no other protein forms quite the same network. Scientists use combinations of xanthan gum, guar gum, and other hydrocolloids to approximate gluten's properties. Let me pose a thought experiment. What would happen if we changed some of the key variables in this system? Without water, the proteins remain in their compact, dry state. They can't hydrate, unfold, or interact. You just have powder, no network at all. If you just mix flour and water without kneading, you get a weak, random network. It has some gluten, but it's poorly organized and lacks strength. If the pH is too high or too low, it affects protein charge distribution and can prevent proper bond formation. Optimal pH is around 5 to 6. Let's think about this from a thermodynamic perspective. Why is the aligned network more stable than the random one? When proteins align, entropy decreases. The system becomes more ordered, which is thermodynamically unfavorable. However, enthalpy decreases even more because the aligned configuration allows more optimal bonding. More bonds form, and they form in lower energy configurations. The Gibbs-free energy change is delta H minus T delta S. Even though delta S is negative, delta H is more negative, so delta G is negative overall. The aligned network is thermodynamically favorable. There are several mechanical properties we can measure to quantify dough quality. Let me describe the main ones. Extensibility is how far the dough can stretch before breaking. This is measured using devices like the extensograph. Elasticity is how much the dough springs back after you deform it. Strong gluten networks have high elasticity. Viscosity describes how the dough flows under sustained stress. This affects how easy it is to shape and handle. Professional bakers and food scientists use rheometers to measure these properties quantitatively. They apply controlled stress and measure the response. Let me summarize what we've learned about this remarkable system. Kneading doesn't just mix. It aligns protein chains and enables dynamic exchange of bonds, creating a progressively stronger, more organized network. Water acts as a plasticizer, providing the molecular mobility needed for the network to reorganize into optimal configurations. The resulting network is viscoelastic, behaving like a solid on short timescales and a liquid on long timescales. The network contains over 10 to the 21st bonds, storing hundreds of megajoules of binding energy. Temperature, salt concentration, and pH all modulate the network's properties by affecting bond formation kinetics and protein interactions. All of this complexity exists to make one thing possible: bread, a material that can trap gas bubbles, expand, and set into a light, airy structure. That's the magic of gluten networks.